Namaste and welcome. There's a secret language that powers literally our entire world, but most of us, we never get to hear it. It's the language of computers, of course. And today, we're going to pull back the curtain and see how it uses some really clever maths to do stuff that, honestly, feels a lot like magic. I mean, just think about it for a second. You've downloaded a file, right? Maybe a movie, a song, whatever. And bam! You get that dreaded file corrupt error. How on earth does your computer know? Did it watch the movie and see a glitch? No way! The secret is actually much, much cooler than that. Okay, so the secret is actually simpler than you'd ever guess. It all comes down to a switch. Yep, a simple switch. A computer, deep down, only knows two things: on or off. That's it. And we just give those two states a name. We call on 1 and off 0. Every single thing on your computer, every photo, every song, every message is just a crazy long string of these ones and zeros. Cello, let's dive right in. If we want to understand how computers can spot these errors, first, we've got to learn to speak their language. And believe me, it's a simple language. It's all about counting, but with just two numbers, 0 and 1. So, this system has a name. It's called the binary number system. You know how we use 10 symbols every day, right? 0 through 9? Well, binary, it just uses 2, 0 and 1. That's why it's called a base 2 system. And this simple idea, it's the foundation for absolutely everything that happens inside your phone, your laptop, everything. And you know what? It's not as strange as it sounds. It actually works just like the math we learned in school. With our numbers, every position is a power of 10, right? You have the ones place, the tens place, the hundreds place. Well, binary does the exact same thing, but it uses powers of 2. So you have the ones place, then the twos place, the fours place, the eights place. Each spot is just double the last one. So let's take a look at a binary number, say 1001. How do we figure out what that is? It's easy. You've got 1 8, 0 4s, 0 2s, and 1 1. Just add it up. 8 plus 1 is 9. See? Simple, right? It's just a different way to write the exact same number. Any number you can imagine can be written in binary. All right, so now we know the language of ones and zeros. Now we can finally solve the mystery we started with. Let's see how computers use this super simple language to become digital detectives, spotting even the tiniest errors in our data with amazing accuracy. The trick they use is called a cyclic redundancy check, or just CRC for short. Now, I know that sounds super technical and complicated, but don't worry. Just think of it like a unique fingerprint for your data. It's a special little checksum that's created from your file before it's sent, and then it's checked again when it gets to the other side. So how is this data fingerprint actually made? Well, it's a pretty neat 3-step process. First, the computer that's sending the file adds a few temporary zeros to the data. Then, it divides this new longer number by a kind of secret password, a special generator code. And whatever is left over from that division, that remainder, that's it. That's the CRC code. So what's the fun to here? How does this actually catch an error? Let's walk through a real example. This is pretty much exactly what's happening under the hood every single time you download a song or send an email. Okay, so let's say this string of ones and zeros is our data. We'll call it D. And both the sending and receiving computers have agreed beforehand to use this specific generator code, which we'll call G. Think of G as the secret key to our whole puzzle. So first things first, the sender adds some zeros to the end of the data. Then comes the really important part. It does this special kind of division using our secret key, the generator code. Now, don't get bogged down in the math on the screen, okay? The only thing you need to know is that this whole process is designed to create a unique result based on our exact string of data. And after all that division is done, we're left with a remainder. For this example, the remainder is 100. And there you have it. This is our CRC code. This is the unique fingerprint for our data. Now, here's the clever part. The sender doesn't just send the original data. Nope. It takes that original data and sticks the CRC code, that 100, right onto the end. This whole package, the data plus the fingerprint, is what actually gets sent across the network. Okay, now for the moment of truth. The receiver gets this whole message, and what does it do? It runs the exact same calculation. It takes the entire thing, the data plus the CRC code, and divides it by that same secret generator code that the sender used. And Here's the magic. If the remainder of this division is 0, it means everything is perfect. It's a match. The computer knows that the data arrived exactly as it was sent, completely untouched, no corruption. But what if it's not perfect? What happens if something goes wrong during the journey? A bit of static, a dodgy cable. Something could flip one of those bits. A 1 could become a 0, or a 0 could become a 1. Let's see what happens then. So now the receiving computer gets a message that's slightly different from what was sent. It doesn't know there's a mistake, of course. It just does its job. It takes this new, corrupted message and performs the exact same CRC check, dividing it by that secret generator code. And look, the remainder is not 0. The moment the computer gets a non-zero remainder, alarm bells go off. It knows instantly that something is wrong. The data doesn't match its fingerprint, and that is when it tells you file corrupt. That's the whole secret. So let's just bring it all together. That file corrupt message, the one that seems so random and mysterious, it's not mysterious at all. It's actually the result of a really simple, really elegant math check that's constantly happening behind the scenes. It's not magic, is it? It's just some very, very clever mathematics. You can think of it like a secret handshake between computers, a way for them to make sure they're hearing each other clearly, even across thousands of miles of noisy networks. Every time you do anything online, this little check is happening, keeping our digital world safe and sound. And that really leaves us with a final thought, doesn't it? We've just learned the alphabet of this secret digital language, and we've learned how computers ask each other a very important question. Are you okay? So if a simple language of ones and zeros can do all of this, it really makes you wonder what other incredible conversations are computers having right now all around us.